Next, I want to introduce the speaker, Dr. Ke-Horng Chen. And I think no matter how many modules or devices are made, the small size, lightweight, and the power consumption, the swap issue is always in our field. So how to build or how to manufacturing a small size devices, it should be a very, very important issue. So as we know, the silicon IC or the minimalistic microwave IC, but how to do a monolithic power IC, I think the next speaker, they will give us a solution. And Dr. Ke-Horng Chen, he received the bachelor, master, and the PhD degree in electrical engineering from National Taiwan University. From 1996 to 1998, he was a part-time IC designer at Philips. 1998 to 2000, he was an application engineer at Avati. From 2000 to 2003, he was a project manager at ACARD, where he was engaged in designing power management IC. He is currently a chair professor with the Department of Electrical Engineering in National陽明交通 University and chief technology officer in ITRI. And he is the author or co-author of more than 2,090 papers and hold more than 110 patents. So let us give a big hand to our speaker, Dr. Chen.
Okay, thanks for Chair's introduction. Good afternoon, everyone. I am Ke-Horng Chen from National陽明交通 University. Today's topic is about monolithically integrated GaN chip. Everyone knows the advantage of GaN, but you do not know the disadvantage of GaNs. In today's talk, I will talk about the disadvantage of the GaN. Why do I need to tell you the disadvantage of GaN? Because if we want to use the GaN in our design and push the GaN into the market, we need to know the disadvantage of the GaN. This is today's outline. In the beginning, I will show you the GaN device and the GaN process. After the introduction of the GaN, I will show you the defects of the GaN. The defects include current trapping effects, self-heating, and backgating effects. Based on these defects, we can find some solution to suppress these drawbacks. Therefore, I will show you some possible solution to suppress these drawbacks. For example, the temperature-compensated controller and phasor turn-on technique. And the second is meta-fast comparison technique, and pre-driving technique, and desaturation technique. And finally, I will make a conclusion. Okay, according to this slide, we can realize the relationship between the cost and the wafer size. The substrate that can be used for the GaN can be one of the substrates. For example, you can use diamond, aluminum nitride, and GaN or SiC or silicon. For the diamond substrate, it has the highest cost but it has the lowest wafer size. In contrast, for the silicon substrate or silicon substrate, it has the lowest price and the largest wafer size. It means that if we have a larger size, the total price will be reduced. For the current product, for the current process provided by TSMC is 60-inch silicon on GaN on silicon process. It can have a good performance, but it still has many defects on this process. On the other hand, if we have the silicon substrate, we can have a good reliability and performance. However, its cost is still high. So in the near future, you will see the process of GaN on silicon change from 6-inch to 8-inch. It means that we can reduce its price, and the possibility of GaN product will be true for today's market. Furthermore, for the GaN on silicon carbide, maybe in 2024, you can get the GaN on silicon carbide process. It means that we can have a reliable process to implement our chip. Okay, so we can conclude that GaN on silicon process will be provided in the near future. Besides, it has a good process quality, but its cost is still high. Next, I will show you the advantage of GaN-HAM. For the GaN-HAM, it has the following advantage. The first one is the high voltage stress. In theory, it can tolerate maybe higher than 1,000 volts. It means that it can be used in high power density, high voltage, and high voltage, high power density, and high switching applications. The second advantage is low parasitic capacitance. It means that if we want to have a high switching operation, its low parasitic capacitance will determine the switching power loss. In other words, low parasitic capacitance means that we can reduce the switching power loss. Furthermore, another advantage is low on resistance. It means that if we can have a low on resistance and with low small chip size, it means that the power conduction loss can be effectively reduced. Based on this advantage, it means that GaN is a good candidate for today's powered electronics because it has minimized switching loss and conduction loss. The last advantage is no reverse recovery charge. It means that compared to most silicon process, the reverse recovery charge loss is large for silicon process. But the GaN device, it does not have the reverse recovery charge loss. Based on this advantage, we can operate the GaN switches at a higher switching frequency to get a high power density and a compact size solution. In this slide, I will show you the available GaN hands in today's market. It includes two types of GaN. The first one is eGaN, and the second is the dGaN. According to their names, it means like eGaN is an enhancement-mode GaN. The other name is normally off device, while the dGaN is the normally on device. For the eGaN device, there are two popular products in the market. The first product is GaN system. The eGaN provided by GaN system. The other one is the product from Navitas. For the product from Navitas, it provides gate driver and GaN switch on the same chip. So it is the good implementation of monolithically integrated GaN chip. On the other hand, if we see the product from the dGaN solution, there are two solutions can be provided by these two companies. One is the transform, one is the cascode structure from the transform. The other one is the direct drive from TI. Compared to these two products, there are different performance because for the transform product, it has the cascode structure. Why do they use the cascode structure? Because if they use the cascode structure, it can make the dGaN become normally off device. But the disadvantage is the GaN drive signal are applied on the MOSFET. It means like the capacitance will become larger. In other words, this device cannot operate at a higher switching frequency. On the other, in contrast, for the TI products, the gate drive signal are applied on the gate of GaN. It means that the operation frequency can be higher than light of MOSFET. It means that it has the advantage of high switching operation and high efficiency. If we compare E-mode and D-mode GaNs, we can find light. Most of people like to use eGaN, E-mode GaN, because it is easy to control it, because it is normally off device. On the other hand, the D-mode is not easy to use, but if you use the cascode structure, the operation is similar to conventional MOSFET. But the switching frequency cannot raise to a high value. But if we compare these two GaNs, we can find their temperature coefficient. Their temperature coefficient are different. For eGaN device, their temperature coefficient are higher than light of dGaN. In other words, if we operate it at high switching operation and high power operation, it will cause the increase of the threshold voltage. In other words, it will induce maybe abnormal aberration or large power loss. Okay. So the new startup company chip GaN semiconductor provides another solution to improve the TS product. The port number is GDP 2 at 15. The product provided by chip GaN semiconductors use smaller current sensing. The current sensing can detect the current flowing through the MOSFET. In other words, it controls the leakage of the GaN to decide the suitable turn-off voltage. In other words, if we use different GaN devices, we can adaptively change the control voltage. In this figure, we can find the threshold voltage from 10 volt discrete to 13 volt, minus 13 volt. Then the leakage current can be reduced to an acceptable value. So the product provided by this port number can have high switching frequency and low leakage current. Similarly, it has the same advantage because the GaN drive signal are applied on the gate of the GaN. So it has the advantage of high switching frequency and high efficiency. After the introduction of the dGaN, I can show you the defects of the GaN. The defects of the GaN. The defects include the first one is the trapping effect and current collapse. What is the trapping effect and the current collapse? When temperature increases, hot carrier injection will induce some electrons are injected into the aluminum gallium nitride barrier and the buffer layer. It means that the 2DG layer will be weakened. In other words, it will degrade the performance of 2DG. On the other hand, if the pulse switch operates at a higher switching frequency, similarly, the electron will be trapped at the buffer layer. In other words, it will obstruct current flow. If these two effects occur, it will see the 2DG layer will weaken over time. It means that on resistance and the threshold voltage will increase. In other words, the efficiency and the control will become difficult and the performance will degrade. Let me show you another defects of the GaN. That is the short current protection. For the IGBT, it is easy to detect the transition between the saturation and the active. While for the thicker device, it is not easy to detect the transition from linear region to saturation region. So at the right-hand side, this figure, there is no clearly defined region. In other words, if the short circuit protection is not applied on this thick device, it will cause abnormal operation or efficiency degradation. Similarly, for the GaN device, you will see the IV curve is deteriorated by three effects. The first one is current collapse. So without defects, you can see the current is at a high level, but if the current collapse occurs, the current level will be decreased. The second effect is key effect. In other words, it will make this transition more smooth, so it is difficult to detect this region. Furthermore, for the device, it has a third defect, that is self-heating. the self-heating. In other words, if the self-heating occurs, it will limit the current driving capability. For the most of the products, we can use shunt resistor, current monitoring, or overcurrent detection for GaN or SiC MOSFET. So we can provide another solution is embedded the shoot-through current detection into one chip. In other words, we can have on chip deset detection to avoid shoot-through problem. The shoot-through problem is for example, for the fabric design. You can easily find light if the shoot-through problem occurs. The primary current, secondary current, and slumber current will appear at the same time. In other words, the energy transfer to the output will degrade. Furthermore, the efficiency will be degraded too. So the product provided by GaN semiconductor, the port number is GPE1627, can provide on chip. So this is the first time to embed it the on chip deset detection. Okay. So let me show you the monolithic integrated GaN solution. This is the GaN on silicon process. So it includes high voltage devices and low voltage devices. High voltage devices include 650 50 volt eGaN, and low voltage include 12 eGaN and dGaN. So in this design, we can apply the field plate design on the heavy device to suppress the current collapse to have a good performance of eGaN. So let me show you another drawbacks of the GaN has, that is reverse conduction. Everyone knows that for a MOSFET, if the reverse conduction occurs, there is it will cause the voltage at VSW to minus 0.6 volt. For the GaN device, the voltage will decrease from according to the voltage you used at the VGS. In other words, if you use more negative VGS, it will cause more reverse conduction voltage. In other words, the pole loss at this low side MOS will increase greatly. On the other hand, there is another defect, is that if we have a more negative voltage at VSW, it will cause the voltage stress higher than 6 volt. It means that the voltage will be damaged. So you can see the reverse conduction loss is very high. So the solution for the gate driver is to control the gate driver current. For the discrete solution, we can change the current to drive the gate of the GaN. For the gate drive current, we need to know the threshold voltage of the eGaN. So for the discrete gate driver, fabricated in CMOS process, it is difficult to realize the threshold voltage of the eGaN. On the other hand, if we have a monolithic solution, we can have a good solution because we can monitor the threshold voltage, the variation of the change of the threshold voltage. In other words, we can monitor it on the same die to detect the change of the threshold voltage to have a good gate drive current. If we want to operate it at a higher switching frequency, we can have a faster comparator. In other words, we can use N-type GaN to design a metastable comparator. So the result is based on the metastable condition, we can reduce its response time less than 0.1 nanosecond. Furthermore, we can see like we can, based on the change of the size, the size of pGaN and LGS to get different LFER to implement our bootstrapping technique. Furthermore, if we want to use the GaN in silicon in automotive applications, it means that we need to use GaN-based gate driver to drive the SiC. That is, we can have a GaN-based gate driver for CMOS. For the CMOS, it has a large dB dt and dIdt. It will cause abnormal operation and large CMTI problems. So if we want to reduce these problems, we can have a SIP solution. In other words, we have one chip fabricated in silicon process and two chip fabricated in GaN process. And it means that we have the SIP solution include one TX and two RX. It means that we have a good solution because we have robust capacitor isolator, and we have improved the CMTI GaN-based gate driver, and we have on-chip negative voltage generator to have a robust driving capability. Finally, I will show you if you want to have a hybrid design in the by the GaN device, it means that maybe we can use the GaN on silicon process, but the silicon process, GaN on silicon process have the defect because the GaN current collapse will occur at the right-hand side. It means that we need to have an isolation. So for this hybrid topology, we need to use GaN on SOI process. Finally, let me conclude today's talk. After we have many study of about the GaN, we can predict monolithic solution can provide higher than 240 watts to fit the USB PD 3.1 specification. Maybe this year or 2023, and the power will be up to 200 to 300 watts in the DC AC to DC converter, and the 6-inch GaN on silicon process will be ready in 2023, and 8-inch GaN on silicon carbide process will be ready in 2024. And the most important function is smaller current sensing will be implemented to monolithic solution. Finally, chip GaN semiconductor makes real monolithic GaN chips possible. Thank you.